Hello, my name is Nima Mohammadi. This is a pre-recorded presentation for the 2024 meeting of the Society for Mathematical Psychology. This talk is titled TINN. In this presentation, I will present my recent project on parameter estimation for diffusion models. In this talk, first I will present some motivation for numerical approximation of diffusion models. Then I will describe our model, which I will focus on in this work. After that, I want to discuss a new method for numerical approximation diffusion model. Finally, in the last part, I will present the results of our method for the simplest diffusion model. Sequential sampling theory is the most widely used theoretical framework in cognitive neuroscience to describe how people make decisions. According to this theory, stochastic process in a bounded domain calculates the decision process, and the first passage time distribution of this process serves as the model's probability function. Generally, the first passage time distribution in sequential sampling models can't be expressed analytically, which makes fitting this model challenging and computationally demanding. Therefore, it is critical for the fields of mathematical psychology to develop effective and general approximation techniques for the first passage time distribution of sequential sampling models. In this work, we use a theory-informed neural network approach for simulating and estimating parameters of the partial differential equation, which is derived from this theory. This methodology does both optimization and approximation simultaneously, while a simulation with a continuous solution and optimization parameter combined. Sequential sampling models assume that a noisy accumulation process is started after presenting and encoding of the stimulus. This accumulation process continues until reaching the threshold. So each piece of evidence can benefit one option and against the other option, which is a kind of forward inhibition. In this model, we have three main parameters: V as drift rate, A as threshold, and T index 0 as non-decision time, which is equal to encoding time plus motor time. If we consider t equal to k, the p function is the probability of accumulating track at points k as time and x as space, and the f function is the distribution of first passage time. Or the accumulation process can be done in parallel for each option. This is well known as the race diffusion model. The accumulation process in race diffusion model can be explained as a stochastic differential equation, and after discretization, it will be like this equation. This is well known as a random walk, where I is the index of each accumulator and Wi is the normal Gaussian noise or Wiener process. This model is approximated numerically based on a partial differential equation called the Fokker-Planck equation. After approximating the probability over a domain by solving Fokker-Planck equation, for calculating the first passage time distribution, we should utilize survival probability. It is calculated as you can see in this equation. Also, we use the trapezoidal rule to compute this integration. Therefore, considering the following relation between survival probability and cumulative first passage time distribution. In this way, we use a neural network with two inputs, t as time, x as space, and an output as p, and also with three variables as additional neurons in our model. Then we train our model with optimization loss function, which is derived by two loss terms. One is the mean square residual loss corresponding to the PD, and another is the mean square error of data kernel density estimation and first passage time distribution that is calculated by approximation solution of PD. Now we simulated data for 10 trials with fixed parameters, as you can see. We extract just the first passage time for parameter estimation. In the first step, like the previous slide, we generated 1,000 trials with fixed parameters, then approximated probability on the domain that is shown in the left figure by using our method. In the right figure, we see the approximated solution at a specific time. In this figure, we see the plot of the survival probability. The first passage time distribution plot is shown in this figure, and also presented exact and predicted parameters in this table, as you can see. In this slide, we estimated parameters 45 times with different values. Our method has some advantages. The computing cost is decreased, the numerical approximation accuracy is raised. This numerical method is a meshless method. Parameter estimation and numerical approximation are domain done together. This project is done under the supervision Amir Hossein Hadian, Mustafa Abbaszadeh, Mehdi Dehqan, and Jamal Amani Rad. Thank you for your time and attention.